When electrons flow through a physical conductor, they face an obstacle. This obstacle is electrical resistance. According to Ohm's law, the current flowing through a wire is proportional to the potential difference applied across it, assuming temperature is constant. But the actual value of that resistance depends directly on the physical dimensions the electrons have to navigate. This diagram outlines the core variables. Resistance equals ρ times length divided by area. Notice the distinction between resistance, which changes if you alter length or area, and resistivity, represented by ρ. Resistivity is a fixed property of the material, completely independent of the conductor's dimensions. We can map this relationship onto a graph, but doing so introduces a common trap. When presented with graphical data, the instinct is often to immediately calculate the slope starting from the horizontal x-axis. This VI graph displays voltage on the y-axis and current on the x-axis, with two conductors, A and B. Because resistance is defined as voltage divided by current, the correct geometric angle for calculating the tangent must originate from the current axis, labeled here as I. If you calculate from the voltage axis by mistake, your physical ratios will be entirely backwards. To find the true resistance, we determine the angles relative to the horizontal I-axis. For line A, the angle is given directly as 60 degrees. For line B, we take the 90-degree quadrant, subtract the 30-degree offset from the V-axis, and find its true angle is also 60. Wait, let's look closer at the notation. Line A is 30 degrees from the vertical, making it 60 degrees from the horizontal. Line B is clearly marked as 30 degrees from the horizontal. We can now resolve the mathematical ratio of resistance A to resistance B. By taking the tangent of these newly identified angles, we get the tangent of 30 degrees divided by the tangent of 60 degrees. That simplifies to 1 over √3 divided by √3, leaving a final ratio of 1/3. Treating graphical data on autopilot leads to inverted answers. Accurate resistance calculations require you to orient the geometry to the physical variables at play. That principle of tracking physical constraints becomes critical when a wire is deformed. If you stretch a closed cylinder, it gets longer, but to maintain the exact same amount of physical material, the cross-sectional area must simultaneously shrink. The total volume remains constant. Looking at this derivation panel, we can find the true relationship between length and resistance. Because area changes alongside length, we substitute area out of the standard equation entirely. Using the constant volume formula, volume equals area times length, we rewrite the resistance equation to isolate length. This leaves us with resistance equals ρ divided by volume multiplied by length squared. The math dictates a strict outcome. Because the material's resistivity and the total volume are fixed, resistance is directly proportional to the square of the length. If you double the length of a wire by stretching it, you don't double the resistance, you quadruple it. Altering one dimension in a closed physical system creates a cascading effect on the other dimensions. This forces a squared mathematical relationship rather than a simple linear one. We can apply this exact same substitution logic to isolate the cross-sectional area. This set of equations details what happens when we remove length from the formula. By substituting length with volume divided by area, we find that resistance equals ρ times volume over area squared. Resistance is inversely proportional to the square of the area. We can extend this logic one step further for wires with a circular cross-section. Since area equals pi times the radius squared, substituting that into our area equation shows that resistance is inversely proportional to the radius raised to the 4th power. For minor physical deformations, specifically those under 5%, we can use a calculus-based approximation shortcut. The exponent in the proportional equation becomes a direct multiplier for the percentage change. A 1% increase in length yields a 2% increase in resistance, but a 1% increase in radius drops the resistance by 4%. Understanding the specific mathematical power assigned to each physical dimension allows for instantaneous, highly accurate approximations in real-world engineering scenarios. This diagram presents a scenario that breaks simple algebraic proportionality, a spherical shell where current flows radially from the inside out. As the current travels outward from inner radius A to outer radius B, the cross-sectional area it passes through constantly expands. Because the area is non-uniform, we must slice the sphere into microscopically thin concentric shells. We define the differential resistance of one infinitesimally thin shell as dr, with a thickness of dx at a distance x from the center. We set up the integral by replacing the area term with the surface area of a sphere, 4 pi x squared. This accurately represents the expanding surface the current flows through. We then integrate this expression from the inner radius a to the outer radius b. Solving the integral of 1 over x squared gives us negative 1 over x. Evaluating from a to b yields the final exact formula for the shell's total resistance, rho over 4 pi, times the quantity 1 over a minus 1 over b. We have now established 3 distinct frameworks for extracting resistance. We extract slope from the precise geometry of a VI graph. We use squared and fourth power scaling laws for stretched conductors, and we rely on integration to calculate resistance across variable, non-uniform geometries. True mastery of physics requires diagnosing the physical constraints of a problem first. Once you define the physical reality, selecting the correct mathematical tool, whether it's simple trigonometry or differential calculus, becomes the easiest part of the process.